And that is the little childish thing that we will be talking about, the Tippe-Top. Those of you who want to have a go, we've got a couple of them around. It's very difficult, actually. Thankfully, I don't have the skill, but my wife does. And the little bit you can see of her is making it work. You started off the way you would think it was stable, but when you spin it, it actually turns over. And it stays like that. This is real time. It stays like that for a little time. And then, of course, eventually, a little bit of friction means that it falls down. If you missed it first time, the most interesting thing about the Tippe-Top, and this is what started the whole theory off, is if you notice it, it's spun one way, and although it turns over, the spinning is still the same way. The spinning does not travel with it. It is independent. If you like, the spinning, angular momentum, if there are any physicists here, stays in place. And this, as we will see, was the prompt to the theory. I'll show you once more. Watch it, spinning that way, and it's still spinning that way, and even now it's still spinning that way. If you look very closely, you can probably see my reflection with the video camera. The TippeTop theory is about the Earth's magnetic field. And this picture by Peter Reed shows that field. The Earth has a North Pole and a South Pole, and the picture puts a magnet on it. If you've ever used a compass, don't worry, they are adjusted to make sure that they point to the geographic north, not the magnetic north, which is actually, as you see, is actually 11 degrees different. Where the theory started from was the thing that's been known to geologists for a long time, geomagnetic reversals. The magnetic field has not always been that way round. The definition of magnetic reversals is a change in the Earth's magnetic field such that the positions of magnetic north and south are actually interchanged. So when that happens, your compass points to the south, not to the north. Looking at through ancient history, the Earth's field has alternated between periods of normal polarity, the one we know now, and reverse polarity when the field apparently was exactly opposite. And the reason that geologists know this is the reversals have left a record in rocks. When rock is molten, it records the current magnetic field. But once rock solidifies, that magnetic record is fixed. Later changes do not affect it. So geologists have seen in the rocks that they're looking rocks that go through the ages, the magnetic field changes. It's like it is today, and then earlier it was the other way, and then back. And reversals have happened quite often. And this is the standard conventional view of reversals. I've taken it from the British Geological Survey. It's believed that the source of the magnetic field around the Earth is the liquid core. Earth, of course, only has a solid outer. Within the core of Earth, and the vast majority of Earth, it's actually molten. And it's believed that iron in the core is the cause of the magnetic field. Typically, the rocks show there are 4 or 5 reversals per million years. Conventional theory says that these reversals have occurred very slowly. Now, there's not much evidence for that, but geologists do point to measurement of magnetism in pottery from Roman times, which suggests that the field then was about twice as large as it is now. And of course, there becomes a massive extrapolation to say, well, if it's been reducing over the last 2,000 years, perhaps it goes on slowly to nothing and then turns over and goes the other way. I worked for many, many years on computer simulations, and it was wonderful to see this statement in the BGS website. The one thing that a lot of people think about computer simulations is they must be right because it's all clever and it's on the computer. I can vouch for the fact that just because you've got a computer simulation, it doesn't mean it's right. And in fact, it's very clear that those building simulations of this realize they're a long way from understanding what's going on. Now, Emmanuel Vilkovsky was one of the first to look at geomagnetic reversals as an issue in terms of astronomical events. Vilkovsky, in his famous book, Worlds in Collision, talked about close encounters between the Earth and Venus, and also between the Earth and Mars, and that those happened in historical times. In Earth in Upheaval, his follow-up book, which looked at the scientific evidence, Vilkovsky suggested that these magnetic reversals were actually caused by these close encounters. And that's the background to where the TippeTop theory came from. A good friend and late colleague, Peter Warlow, was responsible for, I think again, one of his grandchildren or someone opening a cracker and having a TippeTop, and watching its action, he devised what he called the TippeTop theory. So Peter is responsible for the theory. Although it was in some ways, like Velikovsky's theories, way away from conventional thought, it was so well done and documented by Peter that he actually got the theory published in the conventional Journal of Physics in 1978. Peter's argument was that an encounter between Earth and another body of, say, similar size and in close proximity for a brief period would cause magnetic attraction between the two, which could make the Earth turn over just like a tippy-top. The Earth is spinning, and because of its weight, it goes around once a day, but there's a great deal of angular momentum there, and Peter decided that maybe just like the tippy-top, which through its slight inaccuracies of rotation, because we flip it, it doesn't need a lot of force to actually turn it over. And so his argument was, maybe another body coming close to Earth, the gravitational pull of that body could be enough to do the same to the Earth. It would tip over, but just like the tippy-top, the rotation would continue. The major angular momentum would be little affected by the turning over. The leap in faith that Peter took in that was that although the Earth might turn over, the magnetic field didn't. And through that argument, he suggested that, unlike convention, which thinks the Earth is rotating in the same way and the field turns over, Peter's theory was the field stays the same, it's the Earth that actually turns over. And just a picture to explain that, this is the sort of thing that Peter imagined. Some sort of body, similar size to the Earth was the assumption he made, comes by, and of course, from a good way before it gets close, there is some gravitational attraction. That gets closer as the body gets closer, and then as it moves away, the attraction reduces again. And this is an original picture drawn by Peter, which I think is brilliant in explaining the tippy-top and relating that to what he believed happened to the Earth. Here we see 4 phases of the turnover. It starts that way up. It slowly starts to turn over, 3/4 of the way there, and then eventually rights itself up the other way. Now, this was the example that Peter used to explain relatively small gravitational forces turning the Earth over, but Peter also pointed out something else, and that's why these little symbols are drawn. What he argued was, now think of this as the Earth, and believe that cross is the United Kingdom, and the circle is Germany. The blob can be Spain, if you like. Notice what is happening as the Earth turns over. The spinning stays the same, and eventually it comes to this position. Over in that one, the spinning is the way the Earth is. It turns towards the east. The sun comes up in the east on a morning. Germany sees the sun about an hour quicker than the United Kingdom. When you get here, it's still rotating the same way. Imagine the sun still over here. In this situation, the United Kingdom sees the sun before Germany. So Peter said, not only is this a mechanism for explaining geomagnetic reversals, it explains some of the historical record which says that in ancient times, the sun rose in the west, not in the east. Now that was all very well, but a few years after Peter had published his very definitive and detailed paper, a guy called Victor Slabinsky published a major criticism. Now Slabinsky was well versed in this subject, and therefore, if you like, someone who was able to look at it in detail. His background was in satellites, so he ought to have known quite a bit about the physics and dynamics of the situation. But he objected very strongly to Peter's theory, and again, the Journal of Physics published the rebuttal. Slabinsky, and I'll read this because it's the essence of his complaint. Warlow has proposed a sudden inversion of the Earth on its spin axis to explain geomagnetic reversals and other phenomena. A complete analysis of his dynamical equations shows that the torque, the actual turning force to make it happen, required for this inversion is 200 times greater than the value he derives, and cannot be produced by the gravitational attraction of any known cosmic body. In fact, what he went on to say, you'd need a body passing the Earth close, very close, and about 400 times bigger. As no such body is known in the solar system, Slabinsky said it doesn't work. The physics behind this and the maths is quite complicated. I've read the papers, believe me, they are not straightforward. They take a lot of reading and understanding. But thankfully, somebody could understand them. In 1989, the SIS published a restatement of the theory by David Salkeld. It's called Objections Overruled, and that's exactly what it was. It was not only just an answer to Slabinsky, but a further explanation of the maths and the physics, which set the thing out properly. And in doing this, David showed that actually Peter Warlow was about right. The big issue had been... Oh yeah, that's right. Yes, David concluded, a full inversion under purely gravitational torque is theoretically possible in a period not exceeding 14 days. Slabinsky said that wasn't possible. And the reasons were this. Peter Warlow had calculated a minimum and maximum turning force, a particular torque that would need to be applied to turn Earth over. Slabinsky had actually used the minimum value. So that was going to look a little unlikely. But what David pointed out was it wasn't so much that it was just the minimum he'd used. He'd also assumed, and read really too much into Peter's theory, that the turnover occurred very rapidly in one day. What David pointed out was, although there were some errors in the maths of Slabinsky anyway, what the issue really was, you didn't need a larger body, you just needed a bit more time. And David's figure of 14 days as the maximum it might take, based on the minimum torque, actually relates to what Slabinsky was saying. If you remember, Slabinsky said it needed a torque which was 200 times too big. Actually, there's a square in the equation, and 14 is roughly the square root of 200. So that's where David got his 14 from. Not only did David explain this and go through the physics, he produced a rather nice chart to show what the equations produced. This graph shows the number of days it would take for 180 inversion, and plotted along the bottom how close the second body came to Earth. And what David calculated was the effect of that for 3 different bodies. One, the size of the Earth, one that was 10 times smaller, one that was 10 times bigger. Notice, although this is measured in Earth radii, if the body is the same size as Earth, you can't actually get closer than 2 radii. Hence the little bit on the left which says impact. If you come away from that, then the body is very close. Coming out here, it's 10, 20 radii away. To put it in perspective, this is very close. The moon is out here somewhere. It's 60 Earth radii. So the theory did expect a body to come, in astronomical terms, very, very close. But David showed that within this limit, it had to happen in 14 days because otherwise the torque just wouldn't be big enough. So up here, it's only partial inversion. Down here, you could get full inversion. And so if you look at the middle picture, it shows that if a body the size of the Earth did come within, say, 3, 4, 5 Earth radii, then the Earth could turn over in something like 5 days. So David's role in this was really to sort it all out. Peter's theory was quite a good one, and most of what Peter did was actually right. Slabinsky, I think, made most of the errors, but David came along, one of the few people I suspect who could actually do all the maths and understand the physics, and rationalized it and sorted it out. Having said all that, and having read the various papers, I'm not actually convinced that David was convinced. His role here was really in helping a colleague, in seeing that colleague's theory criticized incorrectly and responding to that and sorting it out. But reading between the lines, I don't think David was really on board. And I've just got 2 slides to finish, just to summarize, I think, what was really going on. And these are 2 little bits taken from David's definitive paper on the subject. He mentions in conclusion that a partial turn of the Earth's axis, Earth turning partly but not 180 degrees, is more likely in a close encounter. But I think this is really where David was in his thinking. He mentioned electromagnetic forces ostensibly to point out that he hadn't considered them. But what he said was not excluding the possibility that they would play some, perhaps even a major part in any close cosmic encounter. Although David had sorted this out, I think really he was thinking electric universe is the answer, not gravitational force. But just to show that some members of SIS have tried to take the subject further, one final slide. Some other work has been done. The work done by Peter, by Slabinsky and David all assumed that the Earth was a solid body. Well, of course it's not. It's mostly liquid. And I know our friend Lawrence Dixon did quite a bit of work trying to see what would happen if you assume the gravitational force and therefore the turning force, the torque, actually operates mainly on the surface, and the surface slips over the molten core. And Lawrence pointed out that in that case, the actual surface of the Earth that you're turning has a much smaller inertia, and therefore would need much less torque to turn it. The interesting outcome of Lawrence's idea was that if the core didn't actually move, then the magnetic field wouldn't move. So, as I said, some work was done beyond David, but as far as I know, no recent work has been done on this subject. I think most people have thought that, although it was interesting, David obviously found it interesting, but there are few adherents of the theory nowadays. Okay. Good. Yes, that's the difference, isn't it? Once we talk electromagnetic forces, then there may be a good theory there. The issue was obviously this was all about gravitational force only, and as I said, I don't think there are many adherents to that theory anymore.
If I've got understood your hypothesis right, if the Earth were to topple over, what geophysical forces would come into play, i.e. massive tides, earthquakes because the close encounter, electromagnetic discharges, all these things surely would have happened and would have been recorded, not only geologically, but by any person that lived at the time.
Yes, well, and that's part of the theory behind it all, isn't it? That there is a lot in the historical record which does record that sort of terrific upheaval. Yeah.
Read Earth in upheaval.
Yeah.
That describes the effect.
Yeah, yeah. Peter did actually go in, obviously in half an hour you can't say a lot, but Peter went into some of that. Obviously his work was based on Vilkovsky's theories, and what he was trying to do was show what might happen, and that a lot of the other things Vilkovsky said would have happened in that time.
So this event occurs 4 or 5 times every million years, so...
Well, as far as the resolution of the magnetic record in the rocks can tell you, but clearly that's a very coarse thing.
Yeah.
There are theories that say it may have happened a lot more times, but it just can't be measured. It obviously is a very coarse measurement, magnetism in rocks.
Also, if the method of telling the age of the rock is correct, that could be wrong as well.
Yeah. Well, yes. Yes, it could.
Yeah, the theory says that Peter's theory is that that's what brought the last ice age to an end, because it moved the pole, further south, and therefore the ice melted there.
Yeah.
And formed sort of further round.
Yes, although Peter was linking into the Tippe-Top, which moves 180 degrees, and he concentrated on that. He also did say that there were partial inversions, which of course would explain things like an ice age, or just a polar cap moving. Yeah.
So if that was gravity was sort of electromagnetic, then the planet or the body could be a lot further away from the Earth to create the effect.
Yeah. I think that's one of the things that seems unlikely. As I said, well within the Moon's orbit, possible, but it starts to seem a little unlikely that you have to get that close. Chances of that close and missing.
Just one other question, if I may. I don't want to keep going on. But what about the moon in all this business? I mean, would any close encounter affect the moon, its orbit, or?
Well, just looking at these calculations, if it affects the Earth, it's bound to affect a much smaller body, isn't it? Yeah, yeah.
Read Vilkovsky,
Mm.
was orbiting 35, 36 days a month.
If the moon moved 50,000 miles closer, how high would the tides rise? Has that been worked out? I know it would be a lot higher, but
Mm. Don't know, don't know. Yes, it would be.
Peter Warlow did develop his ideas in a book subsequent to the article.
Yes,
The
yes,
Reversing Earth,
yes, he
which got
did.
a lot more detail.
Absolutely right. Yes.
But incidentally, I've just been rereading Vilkovsky's account of his conversation with Einstein, where Einstein, who was a fan of Hapgood, thought that the body of the Earth could slip over the core, whereas Vilkovsky obviously argued for his own theory.
Yeah.
But he spent many hours discussing it with Einstein.
Yeah, it's. I like that idea because in my own business of gas turbines, I'd actually done computer calculations where we had liquid metal, and the friction does really drop when metal, when you get liquids. So it's a nice theory in terms of what could happen because, the moment of inertia, although of course the solid part of the Earth's on the outside, so its inertia is reasonably large just because of the radius. In total, it's quite a small mass, and even when you calculate its inertia, it is quite small compared with the total. Yeah. Yeah. Okay.